So in this lecture, we will study about binary trees. We have already seen about general trees. What are general trees, their definition, and some of the properties of the general trees. Binary tree are special cases of general tree. In general tree, any node can have any number of children. 0, 1, 2, 3, 4. Any number of children can a node can have any number of children. Okay, a leaf node don't have any child, and any internal node, including the root node, can have any number of children. Okay, this is the general tree. But in the binary tree, we have restriction on the number of children a node can have. Okay, a leaf node obviously cannot have any child, but an internal node can have at most two children. Can have zero. That is, if it is a leaf node, it will have zero child, right? And if it is an internal node, it can have one or two children. Okay, so a binary tree is a tree. So binary tree is a special case of tree, special case of general tree, in which no node can have more than two children. Okay, so a node can have at most two children. If the node is a leaf node, it will have exactly zero child, right? If it is an internal node, then it can have either one child or two children, right? So consider a binary tree T. Okay, this is the binary tree. Here A is the root node of the binary tree, right? So A is the root node, B is the left child of node A, and C is the right child of the node A. Okay, so A is the father of B and C. B and C are siblings. Okay, and node D, H, I, F, and J are leaf nodes, right? And all other nodes are internal nodes. Okay, so this is the definition of the binary tree, the formal definition. A binary tree T is either empty. Okay, so this is a difference between the definition of a general tree and the binary tree. A general tree cannot be empty. A general tree always has at least one node, the root node of the tree. But a binary tree can be empty. Okay, a binary tree T can have no node, right? So this is one difference between the general tree and the binary tree. A general tree will have at least one node, the root node of the tree, but a binary tree can be empty. Okay, so a binary tree is either empty or such that T has a special node called the root node. T has two sets of node, LT and RT. Okay, LT is for the left subtree of the tree T, and RT is the right subtree of the tree T, called the left subtree and the right subtree of the tree T respectively. And LT and RT, that is the left subtree and right subtree, are themselves binary trees. Okay, so they are some examples of the binary tree. Okay, so this is the point A, binary tree with exactly one node, which is the root node. Okay, both the left and the right subtrees are empty. Okay, so these horizontal line shows that these are grounded, or shows that the left subtree and the right subtrees are empty. There are no nodes in the left and right subtrees. Okay, the point B, binary tree with exactly two nodes. We have root node A and node B, which is the left child of node A. So here you can see that according to this definition, uh, the nodes of this binary tree are divided into three parts. The node A, which is the root node, the left subtree, okay, this portion is LT, and the right subtree RT, this portion. Okay, the left subtree has exactly one node, node B, and right subtree is empty. There is no node in the right subtree. Okay, a binary tree can be empty. So here the right subtree is empty. Now example C, binary tree with exactly 2 nodes. So in this example, there is a root node A. Here the left subtree is empty. There is no node in the left subtree, and right subtree has exactly one node, node C. Okay, and the left and right subtrees of the node C are empty, are both empty. Okay, example D, binary tree with 3 nodes. So we have root node A, then we have left subtree of A and the right subtree of A. The left subtree of node A has exactly one node, node B, and the left and right subtrees of node B are empty. Similarly, in the right subtree of node A, we have exactly one node, which is the node C, and the left and right subtrees of node C are both empty. Okay, so the main point is that and that binary tree can be empty. So the left and right subtrees of any node of the binary tree can also be empty. Okay, and the second thing is that the number of nodes, the maximum number of children for any node is 2. A node can have either 0 or 1 or 2 children. Okay, so another example of the binary tree. Okay, the root node of this binary tree is A. The left subtree of the root node, which we denoted by LA, is a set BDEG, BDENG, and the right subtree of the root node denoted by RA is a set CFH, right? The root node of LA is node B. So this is the left subtree of node A, and node B is the root node of this left subtree. And the right subtree RA, and C is the root node of the right subtree RA. Okay, so likewise you can define the root node of each of the subtree. Okay, for example, the root node of the left subtree of the node B is node D, and the root node of the right subtree of node B is E. Similarly, the root node of the right subtree of node C is node F. Okay, and the left subtree of node C is empty. There is no node in the left subtree of node C. Okay, some properties of the binary tree. A binary tree is a finite set of elements that are either empty or is partitioned into 3 disjoint sets: the root node, the left subtree, and the right subtree. Okay, the first subset contains a single element called the root. The other 2 subsets are themselves binary trees called the left and right subtrees of the original tree. Left or right subtree can be empty because each left or right subtrees are themselves binary trees, so they can be empty. The nodes in a binary tree have either 0 or 1 or 2 children. Okay, each element of a binary tree is called a node. Okay, so this is just the division of the previous slides. Okay, another example. The following figure shows a binary tree with 9 nodes where A is the root. Okay, this is the root, this is the left subtree, this is the right subtree. Okay, so you can see that the number of children of node A is 2. For node B, the number of children is 2. For node D, the number of children is 0, so it is the leaf node. For E, the number of children is 1. Okay, there is a left child, but there is no right child. Okay, so remember, you have noticed that we are now talking about the left and right child. Okay, so a node in a binary tree can have at most 2 children. So if there are 2 children, so one is called the left and the other is called the right. Okay, so the first child is called the left child and the second child is called the right child. Okay, while in general trees we have any number of children for a node, so we don't call them left or right, we call them the first child of the node A, the second child of the node A, third child of the node A, and so on. Okay, but since there are only two children for a node in the binary tree, we call them left child and the right child. Okay, we don't call them as the first child or right child. Sorry, we don't call them as the first child and the second child. Instead, we call them the left child, that is the first child, which is drawn at the left side is called the left child, and the second child, which is called at the right side, is called the right child. Okay, so G is the leaf node, so its degree is 0, number of children 0. Okay, C is an internal node and its degree is 1. Okay, there is a right child F, but there is no left child. For F, there are two children, so its degree is 2. Okay, and H and I are leaf nodes, so degrees are 0. Number of children 0. Okay, there are various uses of binary trees, and one of those application and uses are in the representation of algebraic expressions. Okay, so those algebraic expressions which involves only either unary or binary operators. Okay, because a node can have at most two children. Okay, so we can represent unary operators, we can represent binary operators using binary trees, but we cannot represent ternary operators in binary trees because ternary operators means which requires three operands. So a binary tree can have at most two children, so you cannot represent ternary operators using the binary trees. Okay, so see example A. So this is the expression A into B plus C divided by D. Okay, so here the root child is plus. Okay, this for this symbol plus we have the root child. Okay, then at the left we have a complete expression or sub expression A into B. Okay, so star, that is the multiplication, is the root of the left subtree of the plus, and then we have its two operands A and B. Okay, so and similarly for this plus operator, its right operand is this complete subexpression. Okay, so this is a complete subexpression C divided by D. So you can have a complete binary tree or a left or right binary tree. So C divided by D. So this is division is the root node of this subtree, and then its two operands C and D. Right. So you can notice that the symbols means that is the operators star, plus, and division. These are internal nodes of the binary tree. Plus, internal node, multiplication, internal node, division, internal nodes, and all the operands A, B, C, and D are leaf nodes. Okay, so when you represent algebraic expressions using binary tree, operators are represented using internal nodes and the operands are represented using leaf nodes. Another example, okay, example B. Okay, you can see that A plus B plus C plus D. Okay, so you can put various brackets, okay, to signal which addition is to be performed first. So here A plus B will be performed first, then C will be added, then D will be added, right? So this plus will be the root. Okay, so for this plus sign, the left operand is this expression and the right is this expression. Okay, D. So here the right subtree of plus will have only single node D. Okay, and the left subtree will be a complete binary tree representing this sub expression A plus B plus C. Okay, so here plus this plus symbol will be the root of the left subtree. Okay, its right child will be the C, and the left child will be the binary tree representing A plus B. Okay, So a plus b, this plus will be the root of this left subtree, and a and b will be the left and right child respectively. Okay. Example C. In the example C, the same procedure is used. Here, unary operators are also used, minus and plus. Okay. So this minus sign, this is not a subtraction, but this is the sign for an operand. Okay, this plus is also a sign for the operand, right? So these sign operator does not have any left child, they have only the right child. Okay, so minus left child empty, right? And right, there is a right child, one operand a. Okay, so the equivalent expression for this subtree will be minus a, and similarly for this sub expression minus b. Rest of the detail remains same. Okay, so algebraic expressions can be represented using binary tree, and since binary tree can have at most two children, so ternary operators cannot be represented. Okay, some important properties of the binary tree. Every binary tree with n number of nodes where n is greater than 0 has exactly n minus 1 edges, right? So if the binary tree has exactly one node, the root node, the number of edges is 0, right? So if the number of nodes n is 1, the number of edges is 0, right? If there are two nodes, okay, then the number of edges will be 1, right? Then you add one more node. Okay, say you create a right child, say number them, name them. This is node A, this is node B. Okay, now you create a right child for the node B. Okay, and the name of the right child of the node B is C. Okay, now the number of node is 3. How many edges are there? 2, right? Now create a left child D for the node C. Now the number of node is 4 and the number of edges is 3. Okay, so you can see this is very much obvious that the number of edges in the binary tree is 1 less than the number of nodes. So if n is the number of nodes in the binary tree, then the number of edges will be exactly equal to n minus 1. Okay, so this is one of the nice property of the binary tree, and it is very useful, right? And second property, a binary tree of height h, where h is greater than or equal to 0, obviously height cannot be negative. A binary tree of height h has at least h plus 1 nodes and at most 2 raised power h plus 1 minus 1 nodes in it. Okay, so what is height? Height of the tree is equal to the height of the root node. Okay, and height of the root node means the maximum length of the path from the root node to the farthest leaf node, right? So the number of edges between the root node and the farthest leaf node is the height of the tree. Okay, so its minimum value is h plus 1 and maximum is 2 raised to power h plus 1 minus 1 number of nodes. So if you have a binary tree of height h, right, then the minimum number of nodes in that binary tree of height h will be h plus 1 and the maximum number of nodes will be 2 raised to power h plus 1 minus 1. Okay, the examples, okay, the case where the number of nodes is minimum is this. Okay, so here you can see you have the root node, this is the root node, then you have the left child of this node, then this left child of the root node has only the left child, this also has a left child, and so on, right? So in this scenario, you will have a sequential structure. The node have a left child, that left child also has a left child, then again a left child, and so on. So you will get almost a sequential. Another example is when you have only the right child. Root node has a right child, then that node have a right child, then that node have a right child, and so on. So again you will get a linear structure. Okay. So in this scenario, the number of nodes will be minimum. Okay. So you can see that here the height of the tree is, this is the root node. So height of the tree is the height of the root node. And what is the height of the root node? The number of edges between the root node and the farthest leaf node. So in these type of tree, there is only one leaf node. This is the leaf node. The number of edges, 1, 2, 3. So number of edges is 3. So the height of this tree is h. And what is the number of nodes? 1, 2, 3, 4. The number of nodes is 4. That is h plus 1. Right. So if h is the height of the binary tree, then the minimum number of nodes can be h plus 1, and the maximum number of nodes will be 2 to the power h plus 1 minus 1. And in that case, you have the maximum number of nodes in the binary tree. That is exactly, every child of the binary tree has exactly 2 children. Every internal node of the binary tree has exactly 2 children. Leaf node obviously does not have any child. Okay, so root node has exactly 2 children. Okay, this node is an internal node, so this node also has 2 children. Internal node, 2 children. Internal node, 2 children. Internal node, internal node, internal node. Every internal node has 2 children. Okay, and leaf nodes does not contain any. Right. So what is the maximum? What is the number of nodes in such a binary tree where every internal node has exactly 2 children? This is the number 2 raised power h plus 1, sorry, 2 raised power h plus 1 minus 1. This is the maximum number of nodes in binary tree of height h. Okay, and this is also so very easy to prove. Okay, you can see that if there is only root node, okay, then you have only one children. Okay, this is the number of nodes n. Okay, and this is label L, and so obviously the label of the root node is 0. Then you have label 1, label 2, and label 3. Okay, and obviously the label is the basically the height. Okay, so here you forget this. Here at the height of this root node is the distance in number of edges between the root node and the farthest leaf node. All the leaf nodes are at the same level, level 3. Okay, so 1, 2, 3. 3 is the height. So height of this tree is 3. Okay. So, and every level of this tree has exactly 2 nodes, has exactly 2 children except the leaf node, right? So every internal node has exactly 2 children. Okay, so at level 0 you have uh, exactly one child, the root node. At the next level, level 1, you will have 2 more nodes, right? At the next level, that is level 2, you will have, okay, 4 new nodes, 2 into 2. Okay, at the next level, the level 3, you will have 2 to the power 3 more nodes, right? Because at each level, the number of nodes is getting double. So at the first level, you have 2 to the power 0, that is 1. Then you have 2 to the power 1, 2. Then 2 to the power 2, 4. Then 2 to the power 3, that is 8, and so on, right? And this is equal to 2 to the power h plus 1 minus 1 if the label goes up to h. Okay, this is the simple proof. Third property, the height of a binary tree that contains n nodes is at least log n plus 1 base 2 minus 1. Okay, this is the just reverse of the property number 2. Okay, that is, if you take the log of this thing 2 raised power h plus 1 minus 1, you will get this. Okay, so the height of a binary tree that contains n nodes is at least ceiling of log n plus 1 base 2 minus 1 and at most n minus 1. Okay, so now at most n minus 1 when the structure of the binary tree is like this. Okay, and minimum when the structure is like this. Okay, fourth property, for any non-empty binary tree T, if n naught or n0 is the number of leaf nodes and n2 is the number of nodes of degree 2, then n0 is equal to n2 plus 1. That is, the number of leaf nodes is equal to number of nodes of degree 2 plus 1. Okay, that is, the number of leaf nodes is one more than the number of nodes of degree 2. Okay, so the proof of this property is this. Okay, say n is the number of total nodes in the binary tree, n0 is the number of leaf nodes, that is those nodes which don't have any child, n1 is those number of nodes which the number of those nodes which has exactly one child, and n2 is the number of those nodes which has exactly two children. Okay, so n is n0 plus n1 plus n2, right? B is the number of branches or number of edges. Branch or edge is same thing. So B is the number of edges in the binary tree. Okay, and you know that the number of branches or number of edges is one less than the number of nodes in the binary tree. So B is equal to n minus 1 or B plus 1 is equal to n, right? Now see this expression, B is equal to n1 plus 2 n2. Okay, so in the binary tree you see that okay, the number of outgoing edges from a node can be either 0, 1 or 2. Okay, outgoing means the edges which are emanating from the node. Okay, and nodes branches are in this direction from parent to child. Okay, so obviously no edge emanates from the leaf nodes. Okay, edges emanates either from those nodes which has degree equal to 1 or 2. Leaf nodes does not have any outgoing edge, right? Those nodes which has degree equal to 1 has exactly one outgoing edge. For example, this node, the degree is 1. This node has the degree equal to 1. This has only one child, the left one. Okay, so only one edge emanates from it, this one. Okay, and those nodes which has degree equal to 2, for example this one, this node, the degree is 2. Okay, and two edges emanates from it. Okay, the number of outgoing edges is equal to 2 for this node, right? So the total number of branches B is equal to n1 plus n2. Okay, because leaf nodes does not contribute to the number of branches. No edge come out of the leaf node, right? And from the those nodes which has degree equal to 1, only one edge comes out. Okay, so we have n1, and those nodes which has degree equal to 2, two branches comes out. Okay, so we have 2 and 2, right? So B is equal to n1 plus 2 into n2. Okay, now put the value of B in this expression, B plus 1 into n. Okay, so we have n1 plus 2 n2 plus 1 is equal to n, this one, right? So we have simply put the value of B, this is B, okay, in this expression. So B plus 1 is equal to n. Okay, okay, and what is n? Okay, n is n0 plus n1 plus n2. So at the right side of this expression, we put the value of n0 plus n1 plus n2. So we have this expression. Okay, n1 gets cancelled. So 2n2 minus n2, you have n2 and n0, and here at the left side we have plus 1. So n0 is equal to n2 plus 1. So the number of leaf node is equal to number of nodes of degree 2 plus 1, right? And this is true for any binary tree. Okay, some more properties. If a binary tree contains m number of nodes at level L, then it contains at most 2m nodes at level L plus 1. Obviously, because at most, so a node can have a node can have maximum of 2 children. So at the next level, the number of nodes will get double at most. So if there are m nodes at level L, the maximum number of nodes at the next level L plus 1 will be 2 into m. Okay. Another property, since a binary tree can contain at most one node at level 0, it contains at most 2 raised power L nodes at level L. Okay, again, we are talking about the maximum number of nodes. So at each level, the number of nodes is getting doubled. Okay, so at the first level, that is level 0, we have only one node. Okay, then at the next level, that is the level 1. Okay, this is level, this is the number of nodes. Okay, how many maximum number of nodes? 2. This is 2. Then at the next level, level 2, the maximum number of nodes can be 4 to raise power 2, right? Then at the next level, at level 3, the maximum number of nodes, level 3, the maximum number of nodes is 8, that is to raise power 3. Okay, so for level L, the number of nodes will be 2 raised power L, right? So this is about the maximum number of nodes. Okay. Now different type of binary trees. Okay, we will discuss about the classification of binary trees in the next lecture.